Hi, I'm geologist Fred Zelt. I've had the opportunity to study some stone Frank Lloyd Wright buildings as a volunteer over the last couple of years, and I'd like to share with you an exploration of the geology of Taliesin in Wisconsin. Let me share my screen and let's get started. I'm recording from the Trimont in Pittsburgh, Pennsylvania, the design of which was inspired by Frank Lloyd Wright's unrealized 1952 second design for Point View residences. Not only is Mr. Wright's design appreciated by Pittsburghers, including Trimont residents, but as you can see on the right, Mr. Wright's concept of living with a panoramic view of Pittsburgh's point, rivers, and downtown buildings was excellent. We'll talk about the Driftless area, in addition to the building stones and the grounds of Taliesin. This talk was given to staff at Taliesin and Taliesin West on April 17, and it's meant for docents and staff at Taliesin and Taliesin visitors, but it's also meant for people who may not have an opportunity to visit. There are about 100 photos of Taliesin buildings and grounds, along with discussion of the geology, so I hope you'll enjoy the talk. I'd like to thank Ryan Houston for inviting me to visit last November, as well as other staff of the Frank Lloyd Wright Foundation and Taliesin Preservation Incorporated who were there at that time. I thank Henry Hendricks for allowing me to share images of Taliesin in this talk. Thanks to Taliesin Preservation Incorporated for permission to share 2 photos. I'm grateful to the people of Iowa County and the folks in Spring Green for their hospitality. I gave a short talk about Taliesin geology to staff while I was in Wisconsin in November, but an invitation to speak about the geology of Frank Lloyd Wright sites in February by the Harrisburg, Pennsylvania Area Geological Society gave me an excuse to put together this longer slide set about Taliesin. This slide set has about 4 times more slides about Taliesin than the Harrisburg talk, including many images and geologic observations shared publicly here for the first time. Here's a map of the Taliesin grounds. The Taliesin building itself is to the north. Midway Barn has Midway Hill behind it. Tan-y-Deri, the Romeo and Juliet Windmill, and Hillside are also to the southwest. We'll talk about all of those plus other key terrain features. I'll also mention an outcrop on the adjacent Thomas Lloyd Jones farm just off the map on the lower left. Notice that Hillside, the first parts of which were built in 1902 and 1903 with prairie-style architecture, has a footprint oriented north, south, east, west. The buildings at Taliesin in the north have principal azimuths of about 35 degrees and 305 degrees. Taliesin was Wright's test bed for the development of his organic architectural style. Construction started in 1911 as Wright transitioned out of Prairie School designs. Remodeling, reconstruction, and additions at Taliesin continued until Wright passed in 1959. Wright subsequently built many buildings using organic design characteristics that were in Taliesin. Some used stone like Taliesin, but many beautiful buildings from the organic design phase were made of brick or wood. More than 15 years after the start of construction at Taliesin, Wright wrote that his preferred orientation for organic house design was a compass azimuth between 50 and 70 degrees. The azimuth at Taliesin is 35 degrees. But remember that Taliesin is the first one. It's the test bed. It's not within the 50 to 70 degree range, but Taliesin is angled in a similar sort of manner. There's more information about organic design and building orientation in presentations and publications about Wright's stone houses such as Gray Cliff, Fallingwater, and Kentuck Knob, including in sources that will be shared at the end of this talk. Here are some key points. Don't worry if this doesn't all make sense to you now. We're going to cover each of these terms in more plain language and with photographs. We're in the driftless terrain here with flat-floored valleys bounded by hills with moderately steep slopes. The low hills right around Taliesin have outcrops of Cambrian sandstones, which were deposited about 492 million years ago. The Tunnel City Group sandstones here include crossbedding indicating flow directions of ancient water currents of the shallow sea that was here during Cambrian time. Traces of Cambrian water current directions indicate that at least some of the Tunnel City sandstones may have been deposited by tidal currents. The outcrops have been exposed to weathering for a long time. They're deeply weathered with loose sand on them, and they host diverse communities of lichens. Taliesin, the building itself, was built with St. Lawrence Formation dolomitic sandstones and sandy dolomites that were deposited during the latest Cambrian period about 490 million years ago. The St. Lawrence Formation was deposited in a shallow sea offshore of sandy beaches. There are a variety of sedimentary textures. There are white crusts on fracture surfaces displayed on Taliesin walls, and where similar crusts occur in nature in a quarry, they can support a special fern flora. There's a red patina on fire-baked surfaces. St. Lawrence Formation pavers outside the house have been subjected to many decades of weathering, and some have been replaced with similar carbonate stones from younger rock layers. At Hillside, the walls include two sandstones and two dolomitic sandstones or sandy dolomites. There's a yellow-gray dolomitic sandstone from the St. Lawrence Formation, and there's a dolomitic sandstone that's more reddish-brown in color. There are two parallel laminated sandstones. There's a yellowish-gray fine-grained sandstone from the Jordan Formation, and there's a medium-gray sandstone that's coarser-grained, with grain sizes up to medium sand. Those are also Cambrian in age, deposited about 490 million years ago. These parallel laminated sandstones were likely deposited on the upper part of a beach. There are traces of life, but they're sparse. There are sedimentary shrinkage cracks, too. There are sandstone pavers at Hillside with a lot of different colors and interesting sedimentary features. We'll see a sampling of those. At Hillside, the assembly hall was built during Wright's Prairie School phase, and the studio was built later during Wright's Organic Architecture phase. In looking at those, we can see evolution of stonework between prairie and organic styles. We'll look at stone at Tan-y-Deri as well. Sandstone in the foundation there looks a lot like the sandstone at Hillside. Here's a geologic map. The colors show geologic ages of bedrock, and the gold star on the left indicates the location of Taliesin. It's in an area of Cambrian and Ordovician bedrock outcrops. The dotted white line indicates the limit of Pleistocene glaciers that came down from Canada periodically over the last 2.6 million years. Glaciers came well into the northern United States, but Taliesin is in an area that's thought never to have been overrun by glaciers. The lows that are now Lake Superior and Lake Michigan, along with hard Precambrian rock outcrops of the Wisconsin Dome, helped guide glaciers away from the Taliesin area. Glacial sediment is called drift, and Taliesin is within the Driftless area. Locations of Gray Cliff, Falling Water, and Kentuck Knob are also shown. Those are other buildings with significant stone components by Frank Lloyd Wright that I've been able to study. At the end of the talk, I'll share places to learn about the geology of those. Each of these sites is open for public tours. I definitely recommend visiting Taliesin to understand Wright's organic architecture, especially of stone houses he built during the organic phase at Gray Cliff and beyond, including his masterpiece of organic design at Falling Water and his grand Usonian stone house at Kentuck Knob. Inside the heavy dotted line on this shaded relief map is the Driftless area. The gold star indicates the location of Taliesin. The Driftless area has steeper hills than the rolling hills and flat prairies of the surrounding glaciated area. We're going to zoom in now on the Driftless area around Taliesin. Taliesin is bordered to the north by the Wisconsin River Valley. The blue line indicates the flow of water in the valley through time, starting in the upper left before Pleistocene glaciers came. The lower Mississippi is thought to have flowed from north to south. Then, when it came close to Military Ridge, which is high ground held up by Ordovician carbonates resistant to erosion, the flow turned to the east along what's now the Wisconsin River Valley. So before and during early glacial times, the rivers thought to have flowed from west to east. Then, as shown in the center right panel, a glacier eventually blocked that east-flowing drainage so that water backed up in the valleys, forming a lake in front of the glacier. As the lake level rose, eventually, water spilled over Military Ridge. The arrow in the lower left part of the bottom left map shows the water spilling over. Eventually, that spillover eroded down and captured the river drainage. The bottom right map shows that today the Wisconsin River flows from east to west, past Taliesin, then joins the south-flowing Mississippi River. The Wisconsin River has reversed course during glacial times. Here's a closer view with evidence of the drainage reversal. This is such a good example that I used it years ago in teaching folks in Pennsylvania about evidence for glacially caused drainage reversals. The shaded relief map shows the Mississippi River on the left and the Wisconsin River across the center. The white boxes highlight ancient river terraces. They're above the current floodplain of the river. The terraces show the past level of the river, and the terraces drop in elevation from west to east, consistent with the ancient river having flowed from west to east. Also notice that the Wisconsin River Valley itself widens from west to east. That's consistent with the ancient river having flowed from west to east. Look at the tributaries in blue. When tributaries join a river, they typically point downriver. Those blue tributaries seem to point to the east, consistent with the previous river having flowed from west to east. Look at the brown lines along the Mississippi River and Wisconsin River Valley. Notice the curved one above the terrace with the white box on the left. That curved ancient valley edge is thought to reflect the Mississippi River cutting around the corner when the whole river system flowed to the east, when the river was at the level of that terrace. Now the river level is at a much lower elevation. Another form of evidence is how narrow the Mississippi River Valley is near where it cuts through Military Ridge. The narrow valley there is relatively young and hasn't had time to erode into a wider valley as river valleys typically do through time. So there's very good evidence that the Wisconsin River has reversed direction during glacial times and that there are glacially aged sediments beneath the Wisconsin River Valley and adjacent tributaries, including glacial aged lake sediments. This map series is from an excellent talk about the geologic history of the upper Mississippi River Valley by Wisconsin geologist Eric Carson. You can find it on the Geological Society of Minnesota YouTube channel, where it has attracted more than 3,000 views. Before Pleistocene glaciations, the Taliesin area and Wisconsin River Valley are thought to have been part of a large watershed that drained into the North Atlantic Ocean through the St. Lawrence Seaway. Today, Taliesin is part of the south-flowing Mississippi River watershed. Next, we'll take a closer look at the terrain and geology of the Taliesin area. On the northern part of this map, you can see the current Wisconsin River floodplain with a very flat floor. The lower parts of the tributary valleys also have flat floors, partially filled with sediment of glacial age, with more recent sediment on top. Those valleys are flanked by hills with moderate slopes that were never overrun by glaciers. Next, we will look at the geology of bedrock in this area. This map indicates the ages of sediments or bedrock at the surface. Pink and yellow indicate quaternary sediments of glacial and recent ages. Those geologically young sediments were never deeply buried, and they're sediment, not hard rock. The greens and browns indicate Cambrian age rocks that were deposited as sediments about 490 million years ago. There are sandstones, and as we'll see, there are carbonates too. The Wisconsin River and pond at Taliesin are blue, but a different light blue indicates Ordovician carbonate bedrock. The Ordovician carbonates are more resistant to erosion than the Cambrian sandstones, and the Ordovician carbonates tend to hold up the highest ridges around Taliesin. Even though the Cambrian sedimentary rock layers are 490 million years old, we think they were never very deeply buried. There was a study of the level of thermal maturity of marine algal organic matter in Ordovician sedimentary rocks south of Taliesin in southernmost Wisconsin. The low level of organic maturity in those rocks suggests that they were never buried more than 700 meters deep. Those Ordovician rock layers are a bit younger and higher in the stack of sedimentary rock layers than the Cambrian rocks at Taliesin. Adding the vertical distance between the Cambrian and Ordovician rock layers, it looks like the rocks at Taliesin were never buried more than about 3,000 feet deep, even though they were deposited 490 million years ago. Hardness and cementation of the sandstones are inconsistent. Some sandstone layers are well cemented and others less well cemented. For comparison, the hard, well cemented sandstone building stones at Falling Water and Kentuck Knob in southwestern Pennsylvania are thought to have once been buried 13,000 feet deep, 10,000 feet deeper than the sandstones at Taliesin. The relatively dense limestone at Gray Cliff in western New York State probably was once buried under as much as 10,000 feet of rock and sediment, 3 times as much overburden as the strata at Taliesin. Let's talk a little bit about words that we'll use. This will make the building stones at Taliesin easier to understand, I hope. There's a gradation between sedimentary rock types. On this triangle, sandstones made up of sand-sized grains, limestones, and dolomites are end members. The sand-sized grains at Taliesin are mainly quartz with some feldspar. Feldspar will be familiar if you've seen granite countertops. In granites, feldspars are the pink, light gray, or buff-colored opaque grains. Limestones are made up of calcium carbonate, CaCO3. Calcite is the mineral name and limestone is the rock name. Another carbonate is dolomite. Instead of having just calcium, dolomite has magnesium too, so it's calcium magnesium carbonate. Dolomite is the mineral name, but it's also used as the rock name. Dolostone is a rock name that was proposed in 1948, but it hasn't been fully accepted by the geology community. You can see I slipped in using dolostone already for the rock name, and now you can see why. There's a gradation between these different rock types. There can be a dolomitic sandstone or a sandy dolomite. There can be sandstones with no carbonate or with a little bit of carbonate in them. And instead of sandstone, the top of the triangle can be siltstone, a finer grained sediment. Some of the stone at Taliesin is really a dolomitic siltstone, but for simplicity, I'll only speak of dolomitic sandstones or sandy dolomites. Calcite or limestone, originally deposited in the Cambrian Sea, commonly was recrystallized and converted to dolomite. This dolomitization process created microscopic dolomite crystals that generally don't preserve fine details of fossils and sedimentary features. Another thing that happens with carbonates is that they can dissolve in rainwater or groundwater. Think of caves, for example, where carbonates have been dissolved to form the cave. Limestones and dolomites can both dissolve, although it's a little harder for dolomites to dissolve. Waters laden with dissolved carbonate can precipitate or deposit calcite or limestone. Think of cave deposits that have precipitated from groundwater. Magnesium is a component of dolomite, and along with magnesium, there can be a bit of iron in dolomites. A lot of times when dolomites are exposed outdoors to weathering, they develop a buff color because of oxidation of trace amounts of iron. Limestones commonly remain gray in weathered outcrops. The last thing to mention here is that geologic terminology has evolved in the last 100 years. In the early 1900s, some of the rock units in the Taliesin region that now are properly called dolomites, dolomitic sandstones, or sandy dolomites were called limestones, including by geologists. So some of the rock formation or rock layer names are holdovers from that period. A rock name may be the such and such limestone, but it's actually a dolomite or a dolomitic sandstone. I will stick with the current geologic terminology, but don't be surprised if you read things written from the early 1900s that don't talk about dolomites at all. They talk about limestones or sandy limestones. Here's a global map from the Late Cambrian period. Laurentia is a continent that's sitting by itself, surrounded by ocean basins like Australia is today. Laurentia during the Late Cambrian was a little smaller than North America is today. In the closer view of the paleogeographic map in the upper right, you can see the outline of the state of Wisconsin and the location of Taliesin in southern Wisconsin in a shallow inland sea on top of the continental block. There was land exposed to the north that supplied sandy sediment to the Taliesin area. These are geologic cross-sections. The lateral dimension of them is distance along the land, and the vertical dimension is geologic time from old at the bottom to younger at the top. The colors are different rock types, sandstones and carbonates. Inside the red box, notice the St. Lawrence Formation. That's going to be a key formation for us at Taliesin. So is the Jordan Sandstone. A given geologic time would be a horizontal line. In the box on the right, at a given geologic time, we would change from a sandstone laterally into a mixed sandstone and dolomite, or just a dolomite in an offshore transition from a sandy shoreline to offshore carbonates in this shallow seaway. The St. Lawrence Formation is a mix of sandstone and carbonate between the sandy shoreline and offshore carbonates. We'll talk about both the Jordan Formation and St. Lawrence Formation when we talk about building stones. The Tunnel City Group is an older rock unit with a label on the lower right. Shallow marine sandstones of the Tunnel City Group crop out on the sandstone hills around Taliesin. Above the Jordan Sandstone in light blue are carbonates, mainly dolomites, of the Prairie School Group. These are difficult to erode Ordovician carbonates that cap the highest hills near Taliesin. This is the same information, but it's portrayed in a different way. In this cross-section, the vertical scale is thickness instead of geologic time. The dashed lines are timelines, and you can see the transition of nearshore sandstones of the Jordan Sandstone to mixed sandstones and carbonates of the St. Lawrence Formation. This cross-section is highly squeezed laterally. The scale on the lower right shows a lateral distance of 25 miles or 40 kilometers versus a vertical distance of 25 meters or 100 feet. The rock layers are fairly flat, and we don't see these changes in thickness in a single outcrop. Notice the purple staple shapes. Those are meant to indicate microbial buildups. In the Cambrian and before the Cambrian, microbial mats were common, and in places they even formed reefs. At Taliesin, near the equator during the Cambrian, there were microbial buildups, including in the St. Lawrence Formation. We will see examples of lamination in the rock that could reflect microbial mats. Now we're going to zoom in on the area right around Taliesin. We're going to look at the terrain, then the geology, then the terrain and geology together. Here we can see terrain and land use on a satellite image. Taliesin is shown in white along with Midway Barn and Hillside. In yellow, locations of 2 quarries are shown along with 3 sandstone outcrops we will discuss. The Jones Valley is a flat-floored tributary to the Wisconsin River Valley with agricultural croplands. The wooded hills with moderate slopes are capped by Ordovician carbonates. Next, we will look at the driftless terrain from perspectives shown by red arrows, starting in the north. We'll start by looking east from Phoebe Point, which was a favorite vantage point of Frank Lloyd Wright's. Then we will work our way south to the hill behind Midway Barn. Here's the driftless terrain from Phoebe Point looking due east. The Wisconsin River is on the left, and the hill on the skyline is capped by Ordovician carbonates. You can see a little bit of the agricultural flat floor of the Jones Valley. Here's the same spot, but now we're looking to the southeast. Taliesin is in the trees in the middle of the photo on the side of a low sandstone hill. The higher hills at the skyline are capped by Ordovician carbonates. You can see the flat-floored Jones Valley of this driftless landscape in between. Here's a view from Taliesin itself. Notice that what Wright called stickouts of the building stones, with some stones extending a couple of inches from the mortar. Taliesin is the first stone building where Wright used stickouts, and he insisted on their use in many of the stone buildings he designed after Taliesin for clients in North America. In the photo beyond Taliesin, we see hills of medium height underlain by Cambrian sandstone bedrock. Here we're standing on one of the Cambrian sandstone hills just behind Midway Barn. We're looking across the flat-floored Jones Valley in this driftless terrain to the moderate hill slopes beyond. The red arrows on this shaded relief map show the 4 sites from which we observe the terrain. Now we're going to look at a geologic cross-section that combines the terrain and the bedrock layers along a transect indicated by the black line, starting in the north at the Wisconsin River. From there, the cross-section will climb up a hill, then go downhill past Phoebe Point Quarry, past Phoebe Point itself, down to the edge of the Jones Valley. Then the cross-section will climb up on the hill behind Taliesin. That's one of those Cambrian sandstone hills. Taliesin is not on the top of the hill, it's built into the side of the hill. That position is one of the features Wright wrote about a lot, and he used that sort of position in other buildings, including Kentuck Knob. From Taliesin, the cross-section drops down to the pond on the edge of the Jones Valley. From the pond, it climbs up on the Cambrian sandstone hill at Midway Hill, then goes almost straight south, passing near Hillside to the sandstone quarry, then back into the Jones Valley. Here's a geologic map that shows the transect. The pond and river are indicated in blue, but the other light blue indicates bedrock of the Prairie School group. The browns and greens are Cambrian rocks, including the St. Lawrence Formation at the quarry up the hill from Phoebe Point, and the Jordan Sandstone at the Sandstone Quarry to the south. The Tunnel City group, shown in green, forms the sandstone hills from Midway Hill to the Thomas Lloyd Jones farm. Here's the cross-section, extending from north to south, combining a profile of the surface of the land with the rock layers underneath. Pink indicates Pleistocene to recent sediments in the valleys. The bedrock layers include the Prairie School group at the top, the St. Lawrence Formation shown in olive green at Phoebe Point Quarry. The Tunnel City group is at the surface on the hills near Taliesin. Taliesin is on the hillside, not perched on a hilltop. Then the cross-section climbs up and over Midway Hill, which has Tunnel City group Cambrian sandstone. The cross-section passes by Hillside and then heads south to a quarry in Jordan sandstone, ending in the Jones Valley. The rock layers tilt down slightly from left to right, consistent with the regional tilt of the sedimentary rock layers here. Remember, on the regional geologic map, we saw that Precambrian rocks are exposed to the north on the Wisconsin Dome. To the south, there are younger rock layers exposed at the surface, although they're still hundreds of millions of years old. Next, we will look at rock layers in the Taliesin area, starting with the Tunnel City group. Here in gray are rows diagrams showing measurements I made at outcrops of Tunnel City group sandstones. The measurements indicate directions of water currents that deposited sand on the bottom of the Cambrian Sea. The circles indicate the number of measurements at each site, and the petals on the rows diagrams indicate directions of the ancient currents. At Midway Hill, there were 34 measurements, and it looks like there are a couple of main directions of currents. The two directions could be consistent with ebb and flood tidal currents. At Romeo and Juliet Hill and the Thomas Lloyd Jones Farm, I didn't get as many measurements, but the multiple directions of the ancient sea currents there are still consistent with the influence of tidal currents in the Cambrian Sea. This is an outcrop of the Tunnel City group on Midway Hill behind the barn. I don't see any signs that the rock here has been quarried. It looks to me to be a natural outcrop. The rock is deeply weathered. You can see that it's pitted. For the most part, it's not very hard stone. There are harder, more completely cemented layers that form a ledge or overhang. I think this outcrop has looked more or less the same for hundreds or even thousands of years, with a profile that I like to think Frank Lloyd Wright could have seen. Wright wrote about being inspired by the forms of rock strata in outcrops. Read the grammar of the earth in a particle of stone. Stone is the frame on which earth is modeled, and wherever it crops out, there the architect may sit and learn. When I saw this shape, and I realized this may be a shape that Wright saw, it really made me think of some of the cantilevered architecture at Taliesin and elsewhere. Here's the Cambrian sandstone on the hill at Romeo and Juliet Windmill. It's also Tunnel City group, and the outcrop here also appears to be very old. You can see the pitted nature of the weathering. There's a diverse community of lichens. There's loose sand because the bedrock has been exposed for so long that cement binding the sand grains was dissolved or altered and washed away, leaving loose sand grains. Looking closely, there are inclined traces of little ancient underwater sand dunes that migrated on the floor of the Cambrian Sea. The traces are inclined down in the direction of migration of the sand dunes, down current. The three-dimensional nature of this outcrop allows us to see that some currents flowed to the left and others to the right. The indications of multiple ancient current orientations are consistent with shifting tidal currents. Also on the right, notice the diverse lichen community and the mosses. I think this is a very nice natural outcrop. Now let's move to the St. Lawrence Formation. We'll look at the quarry near Phoebe Point. In the picture of the quarry, you can see a rock hammer circled for scale. The rock here hasn't been quarried in quite a while, and the quarry is overgrown. Here's another picture of the quarry. The white stick in the center is 2 meters tall for scale. Notice the character of the sedimentary layers or beds, and remember that this character was important to Wright. Some of the rock layers jut out a little bit. At the top of the white stick are layers that are a couple of inches thick. Those would be easily harvested for use as pavers. Blocks of wall stones would have to be split out of the more massive stone. Where the stone is exposed, it's golden brown in color. On the left, there's a vertical natural fracture that we'll see from a different angle in a later slide. Here's a weathered exposure of the stone. Not only has it undergone dolomitization, but it has undergone weathering of the outside of the rock. On the right is a fresh chip. It's gray on the inside and golden brown on a weathered rind on the outside, where the rock is more oxidized. If you harvested only layers that are a couple of inches thick for use as pavers, those slabs might be mostly weathering rind. Having hit this rock with a hammer in the quarry, I can tell you that the fresh rock is significantly harder than the weathering rind. So those pavers wouldn't be especially strong and hard. And we'll talk about that when we talk about the pavers at Taliesin. Look at the texture here on the left. It's a very mottled texture, a very irregular texture. There could be a couple of geologic origins for that texture. There can be horizontal burrows of sea life here. Also, those microbial mats we talked about that were common in the Cambrian can form a clotted texture. The geologic name for rock with such a clotted texture is thrombolite. I think everyone will know the medical term thrombosis relates to clots. Thrombolytic texture is a clotted texture. This sort of clotted texture is something that we'll be looking for, along with traces of life as horizontal burrows through the sediment. It's hard to see these in the outcrop exposures. Those textures have been more easily seen in geologic studies of the St. Lawrence Formation using rock samples that were cut deep underground in wells and retrieved as cores. Those rock samples had not been subjected to surface weathering. We will look at a vertical rock face. Here's a block of dolomitic sandstone. We looked at a vertical rock face. Here's a block of dolomitic sandstone from the quarry that's laying on the ground, so the surface the hammer's resting on would have been horizontal originally. In the sunlight, you can see traces of long horizontal lines that may be horizontal traces made by living things. A lot of the mottled texture could have been caused by burrowing of living things or thrombolytic microbial texture or some combination of the two. This mottled texture is very common in the St. Lawrence Formation. There was a lot of sea life in the Cambrian. Not all of the life forms are familiar to us today because the Cambrian was so long ago that some of these animals are no longer around. But there was plenty of sea life back in the Cambrian in this shallow sea, and some of the sea life left traces on or in the sediment. This shows some of the kinds of traces life forms left as trace fossils in sediment during Cambrian time. Some sea life walked or crawled on top of the sediment, some burrowed into the sediment to create a safe place to live, and some animals consumed sediment. This slide shows sketches that are meant to be like cross-sections of sedimentary layers. If no life has disturbed the sediment, there might be original sedimentary layers preserved. But if living things start to disturb the sediment, either as vertical burrows, vertical to horizontal burrows, or lots of horizontal burrows, then the original layering is disturbed. With enough burrowing, you can end up with a mottled texture, and I hope this texture is starting to look familiar to you. Here's a rock face in Phoebe Point Quarry. You can see a mottled texture as well as a bit of layering. We're going to take a closer look at two windows shown by the red and yellow outlines. Within the red outline, some original sedimentary layering is preserved, but there's a lot of mottled texture. The original layering is a little bit crinkly. It could be a microbial mat. It's not clear enough for me to be certain of that, though, but it's possible. The mottled texture could be bioturbated, it could be thrombolytic, or it could be both. It's a very common texture in this rock unit. In the yellow box at the bottom, near my fingers, there are some very clear burrows in cross-section. The round burrow cross-sections have sand fills and dark clay linings. Here's an open natural fracture. A cross-section of the fracture is visible to the left, and the hammer rests on a face of the fracture. Remember that limestones and dolomites both can dissolve in rainwater and groundwater as in a cave. Groundwater can also precipitate calcite or limestone. That has happened on this rock face. The fine, bumpy texture that's white where freshly exposed is calcite that was precipitated on the vertical rock face. There are calcite crusts deposited like this on horizontal surfaces of the sedimentary rock layers too. It was nice to see the mosses growing here. Then I noticed a distinctive fern called smooth cliffbrake. The ferns were growing preferentially on these calcite crusts, not on the brown dolomite. Smooth cliffbrake loves calcium-rich calcite and limestone and is known for growing on limestones. It was growing preferentially on the calcite crusts here in the quarry. When I went back to Taliesin, I saw this in the courtyard. The dolomitic sandstones are a golden brown color in the wall there. There is smooth cliffbrake, the same fern as in the quarry, growing out of the mortar in the wall. This mortar must be more calcium-rich than the dolomitic sandstone in the wall. Smooth cliff break is known for doing this in other places too. I've read about it preferentially growing out of wall mortar in upstate New York, for example. It was pretty cool to see this in nature and then in the courtyard. When I was at Taliesin in late March, I noticed a concentration of smooth cliff break growing on walls next to steps between the lower court and the residential wing. Most of the ferns were growing out of mortar or round holes called vugs in the dolomitic sandstone. Vugs commonly have a calcite lining. If you look at the distribution of these ferns at Taliesin, you'll see that there are generations of mortar in Taliesin exterior walls. The ferns only grow on the oldest mortar. Before we leave this view of the courtyard, I'd like to point out that the pavers include gray limestone as well as light brown dolomite. These are replacement pavers, and we'll come back to them near the end of the talk. Also, the large window in the top center of the photo is the garden room window. We will see a view out that window later in the talk. Here's the courtyard again in the golden glow of late afternoon. The golden brown of St. Lawrence Formation dolomitic sandstone in the chimney mass glows, with lots of stickouts highlighting the stonework. We saw this sort of natural layering of stone in the quarry. If we take a closer look on a cloudy day, we can also see the same sorts of white, bumpy calcite crusts that we saw in the quarry. It looks to me like the building stones were laid preferentially to preserve and display these mineralized crusts of natural fracture surfaces. In other stone right houses, you can also see mineralized surfaces on display, for example, in walls at Grey Cliff, Fallingwater, and Kentuck Knob. These geologic features are part of the organic design. While looking at this view of the courtyard, I'd like to take this opportunity to tell two stories that highlight how much visiting Taliesin can help in understanding other Wright buildings. Edgar Kaufman, the client for Fallingwater, visited Taliesin when Fallingwater was in the design stage, and Edgar Jr. served as an apprentice at Taliesin. They may have seen this very scene. I think part of the reason Fallingwater is such a wonderful work of art is that the Kaufmans allowed Wright to build Fallingwater with so many of the organic features Wright intended. Seeing Taliesin, it's easier to understand how that happened. The clients for Kentuck Knob, the Hagans, also visited Taliesin when Kentuck Knob was in the design stage. It's well known that when the Hagans were back in Pennsylvania considering building stones for Kentuck Knob, together with a Taliesin apprentice, they stopped at a second property they owned. There, they saw nondescript gray boulders next to the road. The apprentice had a hammer. When he whacked a boulder and exposed fresh golden brown sandstone, all three of them realized they had found the stone for Kentuck Knob. I was aware of that story, but seeing the golden brown stone at Taliesin and knowing that all three of them would have seen it too makes it very clear why they all realized that they had found their building stone. Moving inside Taliesin, we see the irregular textures of floor and wall stones of the living room. The floor pavers are a different color because they were coated with shellac. There are stickouts inside just as there were outside. If we take a closer look, we see a slab of stone tipped on end over the fireplace with the mottled texture of the stone on display. There are hints of linear features that could be originally horizontal burrows like the ones we saw on the surface of a stone slab in the quarry. Wright used a lot of indirect interior lighting, which makes the sedimentary features a bit more indistinct. There are a lot of fireplaces like this at Taliesin. We will not look at all of them, but we'll see enough of them to get a sense of the variations between them. This is the Gold Room, which is the room where John Lautner stayed as an apprentice. Mr. Lautner went on to become a very famous and accomplished architect in California. Look at the stickouts in the interior wall. This room has a lamp that will enable us to see details of the stone. If we look a little closer, you may notice a red patina on a couple of the wall stones. We'll talk about that later. Look at the view Mr. Lautner had of the driftless landscape through the window. Imagine sitting at this desk facing the Jones Valley, as I did, when a pair of sandhill cranes fly by with their long trilling and trumpeting calls. What a beautiful experience, a gift of nature. Okay, back to geology. Let's look more closely at the fireplace. Again, there's a stone tipped on its side over the fireplace so that we're seeing an originally horizontal sedimentary layer. There's a lamp to the side that illuminates the texture of the surface. I hope you can see lots of linear and curved features here that could be horizontal burrows, but they're not super well defined. Overall, it's a mottled fabric. The other major feature here is round holes called vugs. Those are places where the carbonate was dissolved and removed. Maybe there was a little bit of carbonate there that was more easily dissolved. Vugs are a characteristic feature of the St. Lawrence Formation here at Taliesin. You can see vugs in the wall stones here too. When you see vugs, you start thinking the stone is likely a carbonate. Here's another fireplace, this time on the third level, again with a rock tipped up on end so that you can see the geologic character of it on display in this organic design. This is Mr. Wright's bedroom. Notice that the pavers have very irregular edges. This is typical of stone floors in Wright organic designs. The cheapest thing to do with pavers would have been to have someone chop or saw them into rectangles or squares, all of the same size, making it quick and easy to lay them. But instead, the pavers are unique shapes pieced together like a jigsaw puzzle. With a closer look, we can see the irregular texture of the tops of the pavers, which is the same texture on display here on the originally horizontal stone surface above the fireplace. Here's a closer view of the texture of the stones above the fireplace. It's a mottled texture, perhaps with some indistinct horizontal burrows and maybe a bit of thrombolytic texture. Here's a wall stone block with a mottled texture and a nice vug in the center. Some Taliesin stone blocks have clear burrows, including more distinct horizontal burrows above some fireplaces. I want to show you two more fireplaces to illustrate variations in building stones at Taliesin. Here's a fireplace that's mostly typical St. Lawrence Formation, but with unusually distinct, originally horizontal burrows in the stone slabs above the fireplace. There are also small slabs of pink quartzitic sandstone built into this fireplace in Mrs. Wright's bedroom in several places, making it unique at Taliesin. This is Mr. Wright's drafting studio. You can see there's a drafting table off to the side and a stone fireplace under the portrait of Mr. Wright's mother. We'll take a closer look at the fireplace. In a more detailed photo, we see sedimentary lamination preserved and less of the mottled texture that's typical of other fireplace stones. Again, the stone has been tipped on its side so that the originally horizontal layering is vertical. The increased preservation and smooth shapes of the fine sedimentary layering or lamination make me think that this is more of a fine-grained sandstone than a dolomite. So we've seen that although most fireplaces at Taliesin are similar, they're not all the same in detail. Here's another view of Mr. Wright's drafting studio at Taliesin. Notice the stone stickouts on the interior here, and look how the built-in on the left was built around the stickouts. That's a common design feature in other stone Wright houses from the organic period. Here's a view of another built-in that is better illuminated. You can see that the built-in accommodated the stickouts like built-ins do in other stone Wright houses. Here's the loggia area. Notice the irregular outlines of the pavers. Look at the different colors of wall stones on the upper left. We'll take a closer look at that area. Some of the wall stones are dark red. I mentioned that dolomites often have some iron incorporated in them. When baked, that can form iron oxide, and that's likely the origin of the red patina we're seeing. There were two major fires at Taliesin and at least one lesser fire. Some of the fire-baked stones were incorporated into rebuilding and extensions of Taliesin. Stones with red patinas are scattered around, as we saw in the gold room. I mentioned earlier that we would see a view of the courtyard from this window in the garden room. You can see nice stickouts of the golden brown St. Lawrence Formation, and that the window includes mitered glass in the corner. The window glass is set into the stone wall without a frame. Making windows very transparent to blur the boundary between inside and outside is a common organic design feature of Wright's. On the shelf, there are natural objects, including a couple of geodes. But there's another special geologic feature just to the right of the box on the shelf. If we turn around and look in the opposite direction here in the garden room, we see this view. Displayed in an opening in the stone mass is the same sort of geologic feature. To a geologist, these objects are clear indicators of a desert environment, like the Arizona desert at Taliesin West. These are crystals that grew in sand in an arid environment. The crystals are probably a sulfate, such as gypsum or selenite, or possibly barite. Where such crystals grow in pink sand and have a round shape, they're called desert roses. To me, these desert objects form a tie to Taliesin West. I wanted to point out diamond-shaped windows at Taliesin. Wright used diamond shapes in highly stylized windows in some Prairie School houses. He helped design a school in Japan in the late 19 teens and early 1920s that had a large diamond-shaped window. The diamond-shaped is an important theme at Graycliff. There, Wright's flattened or rhomboidal diamond shape that fit and mirrored roof lines found an organic tie to naturally occurring geologic shape. If you watch the talk or view the publication about Graycliff Geology, you'll see that the diamond theme at Graycliff, the diamond window, and the organic tie to naturally diamond-shaped boulders is expressed. I wanted to highlight that these diamond-shaped windows at Taliesin, I wanted to highlight them because they're very special to the geologic organic theme elsewhere. Corner windows with mitered glass are another organic design feature of Taliesin and other Wright houses that relate to the natural landscape setting. The mitered glass allows the view of nature not to be blocked by something in the corner. And this slide also provides another opportunity to share with you a couple of really neat views at Taliesin, looking out into the driftless landscape, views that Wright and others would have seen. Now we move on to Midway Barn. I see two different colors of stone. One is reddish brown in color. The other is more light grayish brown with more sedimentary layering preserved than we've seen elsewhere in the St. Lawrence Formation. I'm not going to talk more about this. I just want to point out that there appear to me to be two kinds of stone here. The reddish brown one is a lot like one of the types of wall stone we'll see at Hillside. If we go down and around the corner of the barn on the right, there's a low sandstone wall with an interesting texture. A sandstone block on top of the wall down there is beautifully bioturbated. I hope you can recall the sketches of trace fossils and bioturbation we saw earlier. Weathering of this sandstone has brought burrows out in three-dimensional relief. It's a very natural organic texture. The sandstone quarry to the south is in the Jordan Formation, as you can see on the cross-section. In the photo, you can see slabs of sandstone sitting in the quarry that were never used. This is the upper of two benches in this quarry. There's a stack of sandstone slabs with a mason hammer for scale. Because of the stacks of slabs, we can view the rock without disturbing the ground in this overgrown quarry. Notice the very planar parallel lamination in sandstone here. This photo includes sandstone that's been weathered and is a bit delaminated. There's also parallel lamination below the delaminated sandstone, but the parallel lamination there is not as clear. When sand grains in a sandstone are very well sorted without laminations of silt or darker materials, it can be difficult to see laminations. Planar parallel lamination is a major feature of the sandstone of the Jordan Formation in the quarry. Here's a sandstone in the quarry that has a less common feature. There's a pencil for scale and sand-sized grains that weather with a rust color. The grains are probably a sedimentary iron mineral such as glauconite, which is originally green where not weathered, and is common in these shallow marine Cambrian sandstones. Here's a sandstone block in the quarry. Notice on the right side view of well-defined planar parallel layering that originally would have been horizontal. On the left, we see the top or base of the sandstone block. There are small sandstone ridges that intersect at particular angles. Here we see them along with round features that could be cross-sections of vertical burrows of living things. Although the ridges could be burrows, I think they're probably sedimentary shrinkage cracks, and I'll show you why I think that in a couple of slides. This organic texture is of particular interest because it's featured in building stone at Hillside. Before we leave the quarry, here's another view of one of those slabs. You can see green mudstone between golden brown sandstones. When we take a closer look at that, you can see some irregular features. Some of these, I think, likely are burrows of living things, and others could be shrinkage cracks in cross-section, like the ones we'll talk about next. Here are sandstone steps at Hillside. This area is part of the older part of Hillside, built in about 1903 during the Prairie phase. The circled stone is on the threshold of the steps, a place people would have stepped across to get in or out of this door. So the stone is in a prominent spot. It has prominent features on the surface of it, similar to features we saw in the quarry. There are small sandstone ridges that form intersecting straight line segments. But this block is really helpful because the small ridges transition into features that look like polygonal shrinkage cracks. Mud cracks may be a pattern of sedimentary shrinkage cracks familiar to you. Mud cracks can form when wet mud dries in the air. A water current can then bring sand over the top of the mud, filling the cracks with sand. A similar texture can be formed by variations in salinity of water. Sediment deposited with one salinity can shrink and crack if water of a different salinity flows over it. The underwater shrinkage cracks can then be filled with sand carried by a current over top of the cracked sediment. Sometimes sedimentary shrinkage cracks are difficult to differentiate from burrows. There can be burrows that look like small sandstone ridges, but in this block you can see a transition from polygons that appear to be clear sedimentary shrinkage cracks to the small raised ridges. So I think at least some of these features are sedimentary shrinkage cracks. Here's a prominent display of this organic geologic feature at Hillside. This stone was tipped on end so that the originally horizontal sedimentary layering is vertical. On the right is a close-up, including carved letters on the top and bottom. In between are a pencil for scale and the same texture we've been seeing, which must have been a very special texture to the people who built Hillside. There are very similar sedimentary shrinkage cracks on some shallow marine sandstone pavers and wall stones at Falling Water, especially on Lillian's Terrace and the patio beside the pool. They're shown and discussed in the publication about Falling Water Geology. Here's a typical view of Hillside from the south, looking from Wisconsin Route 23. Most of this structure is a part of Hillside that was built during Wright's Prairie School phase. We'll see rough facings of wall stones in this older part of Hillside, but we will also see that in this Prairie School part, there's finished stonework consistent with finished, stylized prairie design features. This is on the other side of Hillside in the driveway area. This is also the older part of Hillside, distinct from the younger parts, including the studio, that were built after Taliesin during Wright's organic design phase. Again, we see the rough stone faces, but look at the finished corners, and there are no stickouts. Notice the color change in the walls. Also notice that there are stone pavers. We'll talk about both of those. The darker stones on the bottom of the wall next to the Hillside driveway are dolomitic sandstones or sandy dolomites. The lighter stones in the upper part of the wall are sandstones. In the close-up on the bottom, notice the vugs in the dolomitic stones. There are no vugs in the light-colored sandstones. This closer view shows a prominent vug and a white calcite crust on the dolomitic sandstone. The two blocks at the top of the photo on the right are sandstone, without vugs. This wall next to the driveway at Hillside shows 4 types of stone. On the corner, there are gray sandstones that are parallel laminated and have sand grains as large as medium sand. I haven't yet seen that sandstone in a quarry. There are also lighter yellowish to brownish gray parallel laminated fine-grained sandstones, just like the Jordan Formation in the sandstone quarry. There are fine-grained golden brown dolomitic sandstones and sandy dolomites, just like the St. Lawrence Formation at Phoebe Point Quarry and in Taliesin. And there are reddish brown fine-grained dolomitic sandstone blocks, like some of the stone at Midway Barn. I've not noticed the reddish brown stone in a quarry yet. Let's take a closer look at this part of the wall. There's a pencil for scale. Notice the lamination in the light brown dolomitic block in the center. The lamination is a bit crinkled and it could have been formed by a microbial mat. Also, please remember that for simplicity, I'm calling these dolomitic sandstones, but some may be finer grained dolomitic siltstones or silty dolomites. Here's a finished corner we saw previously next to the driveway at Hillside. The planar parallel lamination of the sandstone is well exposed, similar to what we saw in the Jordan Formation sandstone quarry. Here's a more weathered sill where you can see planar parallel lamination that's delaminating like the sandstone we saw in the quarry. There are small burrows in some of the parallel laminated sandstone blocks. This is a sandstone block on the north end of the studio. There's a pencil for scale. It's pretty small scale burrowing, but it does occur along with good planar parallel lamination. There are similar burrows in some other blocks of both the fine-grained light brownish gray sandstone and medium gray sandstone. I think a likely depositional environment for the parallel laminated sandstones at Hillside and in the quarry is the foreshore of a beach. This schematic diagram shows the part of a beach where the waves wash up and down and you get planar parallel lamination, well-sorted sandy sediment, and can have some burrows made by living things. That is the foreshore of a beach, the likely candidate for the environment where sandstones of hillside walls and the Jordan Formation quarry were deposited on the margin of the Cambrian Sea. Now we'll move inside at Hillside. This is the Hillside Assembly Hall, which was built during Wright's Prairie School phase. Notice that the stone here has irregular faces, like Wright used later in his organic design phase, but there aren't stickouts. Notice the finished corners. We'll take a closer look at the fireplace. Smooth, finished stone here has letters carved into it, and carved finished corners are visible. In the same complex of buildings at Hillside, just down the hallway in the studio, is a fireplace that was built during Wright's organic design phase. The faces of the sandstone blocks here are rough. There are stickouts, and there are no carved finished corners. The wall stones are a mix of blocks and slabs. It's wonderful to have these two stone Wright fireplaces so close together, making it easy to compare and contrast work from Wright's prairie and organic design phases. The fine-grained sandstone pavers in the Hillside studio have irregular outlines, many shapes, and are put together like jigsaw puzzles, as we saw at Taliesin. The pavers have a lot of different and interesting sedimentary structures, including parting lineation created by alignment of sand grains in the paver on the right. There are pavers with trace fossils, sedimentary shrinkage cracks, and more. The sandstone pavers have a variety of colors too. The natural features displayed on the pavers are very organic. Here's a view outside of Hillside. I'm told that the stones of the patio on the right may have been added after Mr. Wright's time, but still the geology of these is great. For example, the straight parallel ripple marks on a paver in the foreground on the bottom right suggest wave ripples, perhaps from a beach or tidal flat. Now we're back in the courtyard at Taliesin. We'll look at the pavers in the courtyard area. These steps to a higher level in the courtyard appear to be original St. Lawrence Formation stones. Look at the surface, the nature of the surface, with distinct horizontal burrows. Down lower in the courtyard, there were pavers that the preservationists had to replace. It was impossible to preserve the weathered dolomite pavers when they needed to be regrouted. We talked about the weaker crusts of weathering rinds and thin slabs in the quarry. The weathered original pavers were too fragile to be preserved, so another carbonate was used. The replacement pavers have irregular outlines honoring the original design. They have some really neat features in them. The brown part is probably dolomitic, and you don't see fossils in that part, but the gray part is limestone. In the limestone, there are lots of fossils. There's a pencil for scale. They're small, but the abundant circular fossils here are disarticulated parts of the stems of crinoids, which are echinoderms, commonly called sea lilies or feather stars today. There's a fairly diverse assemblage of marine fossils, including branching and lace-like bryozoans, corals, and brachiopods. This fossil assemblage is not found in Cambrian rocks, but it's common in younger Paleozoic sedimentary rocks that are exposed farther south. If you want to look at fossils and don't mind getting down on your hands and knees, there are lots of little marine fossils in the gray limestones of the courtyard pavers. The Loggia Terrace is another place where St. Lawrence Formation pavers are exposed to weathering, and they needed to be taken up for regrouting and weren't able to be preserved. But as you can see, the organic nature of the design was preserved through the unique and irregular shapes of the replacement carbonate pavers. Tan-y-Deri has a sandstone foundation and chimney. We'll take a quick look at the foundation. Tan-y-Deri was built during Wright's Prairie School phase. We'll look at the area outlined in yellow, the top of the wall where the white arrow is pointing, then the side of the foundation wall indicated in red. Look at the planar horizontal lamination, just like we saw in the Jordan Formation. It's the same sort of sandstone we saw in the quarry and at Hillside. The top of the wall has a texture similar to the interpreted sedimentary shrinkage cracks. Maybe some of these could have a burrowing component, but it's a similar sort of texture. Around the corner, On the foundation, there's sandstone with very nice planar parallel lamination, just like the sandstone at Hillside, a stone familiar to us now. I hope you've enjoyed learning a bit of the geology of the landscape, bedrock, and building stones at Taliesin. I'd now like to turn to sources of additional information. I mentioned 3 other stone Wright sites I've had an opportunity to study. Each was built during Wright's organic design phase after Taliesin, starting with Graycliff in western New York. The other 2 sites are Fallingwater and Kentuck Knob in southwestern Pennsylvania. During the pandemic, as a form of public outreach, Dr. Phil Stokes, the director of Penn-Dixie Fossil Park in western New York, made a video about Graycliff you can find on YouTube. Penn-Dixie Fossil Park is only about a 10-minute drive from Graycliff, and the 2 sites make a great combination. Most of the wall stone at Graycliff is a gray Middle Devonian limestone loaded with marine fossils. That limestone layer and adjacent strata loaded with fossils including trilobites are at the surface and ready for fossil collecting in Penn-Dixie Fossil Park. Graycliff and Penn-Dixie even collaborate on special Wright Rocks tours once or twice a month in the summertime. Here are 3 talks I've given that are available on YouTube. The top one was hosted by the Western Pennsylvania Conservancy as a Fallingwater webinar. It was recorded in April 2024, is meant for the public, and is the first public talk that focuses on the geology of Fallingwater. You can find it through the Fallingwater website or YouTube channel, or by Googling Fallingwater Geology. The next 2 talks were presented to a geological society, so they use more geology terminology without explanation. The first one was recorded in October 2024, and it covers aspects of Fallingwater geology in greater detail. The talk at the bottom includes Fallingwater and Graycliff geology, and to my knowledge, it's the first public talk about the geology of Taliesin and Kentuck Knob. The Taliesin part has about a quarter of the slides that are in this talk about Taliesin. The middle and bottom talks can be found on the Harrisburg Area Geological Society YouTube channel, or by Googling Graycliff Geology, Taliesin Geology, or Kentuck Knob Geology. This is a publication about the geology of Fallingwater that's a chapter in the 2023 Geological Society of America Field Guide 66. A chapter about the geology of nearby Ohiopyle State Park also helps with understanding Fallingwater geology. You can find the guidebook online where it's available for purchase in paper or as a PDF. Alternatively, a library near you with a geology collection may have a relationship with GSA and be able to obtain a PDF version. The first published geology guide to Graycliff is a chapter in Geological Society of America Field Guide 71, which was just published in March 2025. As I speak, the paper guidebook is available through the GSA website. I think eventually a PDF version will become available too. There's a talk about stone Wright buildings with a focus on Graycliff presented at the Geological Society of America Northeastern North Central Section meeting in Erie, Pennsylvania in March 2025. The talk abstract is available online, and the slide set should be posted on the online meeting website along with the abstract. There's a new book in the works about geologic aspects of Frank Lloyd Wright architecture based on the interesting and insightful recent dissertation by Netherlands architect Frans Sturkenboom. I hope you've enjoyed learning about the Driftless area and the geology of Taliesin. Now you also know places where you can learn about the geology of some other Frank Lloyd Wright sites. I hope you have a chance to visit these great places. Each of them has tours available. Take care.